I'm Jonathan Crandall. You've seen me in such fine quality, epic physics educational videos, such as Canu, Physics, Chapter 9A, Work, and Canu, Physics, Chapter 9B, Energy, Kinetic, and Potential. Alright guys, we're rounding out 9C. In 9C, we're looking at total mechanical energy. When we look at a system, and that has to be defined as to what is a system exactly. We look at the total energy that is in the system. How do we define it? We could look at a car engine and say that's a system. We could look at a rock that's on top of a hill and define that as the system. Okay? So it really depends on how that system is defined. But for us, we're going to go ahead and we're going to look at mechanical energy, where we have potential energy plus kinetic energy, where PE is potential energy, KE is kinetic energy, which now talks about the conservation of mechanical energy. Now, for this, we're going under the assumption that no energy is lost whatsoever, that the energy is completely conserved. In reality, do we end up losing energy out of a system? Yes, actually you do. But this kind of gives us an explanation on the ideal situation. Okay, it doesn't mean that the law of conservation of energy has been ignored. It's just the energy has been changed into something else. So we're not violating the law of conservation of energy. But for us here, we're going to look at that the energy is conserved. So whatever our initial KE and potential KE are, let's give it a value of 1 joule, for example. Then in the final situation, the KE and PE of our final will also equal 1 joule. Okay? So that's the idea that we're looking at. So now we have here a problem. And we said Caitlin, Sarah, and Brittany know 3 things. Edward the vampire lives in a tomb that has a height of 5 meters from the ground. Okay? The tomb is next to a cliff that has a height of 1,000 meters from the ground. And there is a 15,000 kilogram rock at the top of this cliff. Now, the first question is, well, what is the kinetic energy of the rock as it reaches the roof of the tomb? Ignore air friction. What is the velocity of the rock as it reaches the roof of the tomb? Again, ignore air friction, because that's where reality comes in and you're going to lose some of that energy overcoming that air friction. That's why we are saying ignore air friction. Okay, well, probably looking at drawing the problem would be a good idea. So here's our cliff. It's 1,000 meters. We have this big giant rock of 15,000 kilograms. That's very, very, very massive. And we have a tomb here down below of Edward the Vampire of Twilight fame, in case you are wondering, where the height is 5 meters. So we go back to the problem and it says, what's the kinetic energy of the rock as it reaches the roof of the tomb? Okay, so when it reaches the tomb, alrighty, so the first thing we got to find out is, well, this rock has potential energy. This is our system. This rock has potential energy. Okay, hang on, let me see. Looks like not everybody is. Let me see if I can get this. Okay, that's a little bit better. So now you guys can see the rock that's on the top here. It's just a little bit. There we go. So you see the rock that's here. You see the tomb here. Here's your 1,000-meter drop. So what we can do, we can calculate the potential energy of the rock that's up here based off of the 1,000 meters. Well, what's potential energy? Well, potential energy is equal to mass times the acceleration due to gravity times the height. Okay, Now, keep in mind, we can easily figure that out as I go get my calculator here for a moment. Just bear with me on here. Okay. I knew I should have remembered that calculator. All right. So with that, so we got P equals mgh. So let's see how much that is. We have 15,000 times 9.8, okay? So we'll have 15,000 multiplied by 9.8 multiplied by 1,000. Okay? And we walk away with this unreally huge number, 147, and then we have 6 zeros following after that. That's how many joules that this rock has. That is the potential energy at 1,000 feet. Okay, now, let's take a look at this. This rock drops. The moment that the rock drops, potential energy is going to be changing to kinetic energy. Why? Because the rock is moving. Remember the definition of kinetic energy, it's moving energy. So let's say at the 500 meter mark, what is the potential energy going to be? Well, it's going to be exactly 1/2 of this, isn't it? Because it's halfway down, that means half the potential energy has been spent and has been changed to kinetic energy. So I'm going to go ahead and say now we have potential energy and kinetic energy. Our potential energy is 7, 3, 5, 1, 2, 3, 4, 5. So this is how many joules of energy we have for potential and how many joules of energy we have for our kinetic. Wow, that's quite a bit. Now, by the time, just before it reaches the ground, okay, the potential energy is going to be near zero because that energy of position, gravitational position, it's almost spent, and the kinetic energy would be at its maximum. Okay, but the reality is we're only interested in what happens here. What is the kinetic energy here? Okay, so what we can do, we know what the potential energy is here. Okay, we know that. Could we subtract the potential energy at 5 meters? Calculate this, the potential energy at 5 meters, subtracted from this. Whatever the difference is, that's the kinetic energy at 5 meters. I think that would be reasonable. I think so. Okay, now some people would say, well, why did you bother talking about this? Well, remember, the idea is conservation of mechanical energy. So I wanted to show you here, maximum potential energy, 0 kinetic. Halfway through, it's split evenly. By the time it reaches the bottom, the potential energy is practically 0, and the kinetic energy is at its maximum. Okay? So let's go with it. We're going to go ahead and we're going to calculate what's the potential energy 5 meters of the ground. So we're going to use the same equation. So I'm going to go ahead here and I'm going to say, here's the potential energy at 5 meters. We're going to use the same exact formula. Mass times gravity times height. So we're going to have 15,000 kilograms multiplied by 9.8 for the gravity multiplied by 5 meters. So now we have that. So 15,000 times 9.8 times 5 meters. And we walk away with 735,000 joules of potential energy that is now left here. So by the time the kinetic energy comes, by the time the potential energy starts here, by the time it gets to the 5 meter mark, okay, this is how much potential energy is left. Okay, that's not a lot compared to what we were starting with, right? So now let's go ahead and we're going to do a subtraction. So I have to go back and remember what I wrote. I have 147 with 6 zeros, okay? So I have 147 with 6 zeros, excuse me. That was the joules. That's the potential energy at 1,000 meters. Now, notice I'm writing this out so you guys can see it. Now, we go back, and what's the potential energy at 735, at 5 meters? It's just merely 735,000. So, in other words, we're going to subtract 735,000 joules. Now, that's the potential energy at 5 meters. Here, let me erase that. It looks like an S and an M. So it's at 5 meters. So that's what we're looking at. Now, why are we doing this? We're trying to find the kinetic energy, folks, because that was our first problem. Going back, that is, what is the kinetic energy of the rock as it reaches the roof of the tomb? I know I'm taking more time explaining it, but I'd rather do that explanation, okay, than take that extra time, do the extra explanation, than leave you guys walking away confused. 147. Okay, so now that leaves us, and I'm going to put this red, okay? It's going to be 146,26500. That's how many joules of kinetic energy, okay, at the 5 meter mark. At the 5 meter mark. So we answered our first question. Our first question was, what's the kinetic energy of the rock as it's touching the roof of Edward's tomb? This is it right here. And now if you're wondering about who's Edward, think Twilight. Okay? It's a very, very old problem that I did. Okay? So about 14,626,500 joules of kinetic energy at the 5 meter mark. So that's part A. Now part B, it says, what is the velocity of the rock as it reaches the roof of the tomb? Again, we ignore friction. Okay. Well, when we look at this, I'm going to switch to another color. So now we're going to look at the velocity. Well, what do we know about the velocity? We know it has something to do with the kinetic energy. So let me close this off. I know that kinetic energy, the formula is 1/2 mass times velocity squared. So I'm going to need to rearrange the formula a bit. I'm going to go ahead and I'm going to multiply both sides by 2 to get rid of that 1/2. So I get 2 times the kinetic energy is equal to mass times velocity squared. Okay, and notice I'm not plugging in the numbers yet. I'm just working through the formula. All right, I'm going to go down here and I'm going to divide both sides by mass. So I go with 2 times the kinetic energy divided by the mass is equal to the velocity squared. All right, now our last part of the formula, we're going to take the square root of both sides of 2 times the kinetic energy at the 5 meter mark divided by the mass of the rock, and that's going to give us the velocity in meters per second. All right, now let's see what we have here. This is our kinetic energy, so we can double that. Okay, so 14,626,500 times 2. Okay, that's a huge number. All right, and we're going to divide that by 15,000. So what we have here, if we punch in the numbers, so I multiplied 2 multiplied by 14,626,500. This is our energy, Okay, this is the kinetic energy at the 5 meter mark. We're multiplying it by 2, and that's going to get us 2,000, oops, sorry. Okay, 29,253,000 joules. Okay? So now we can go ahead, I'm going to outline this in green. 29,253,000 divided by 15,000 kilograms, because remember, we doubled our energy. Okay. So I'm going to divide that by 15, 1, 2, 3, and that's going to equal 1950.2. We're almost done, because ultimately that is equal to V squared. That's what it is. And that's showing you how we did it on the steps here. Because I went ahead and I calculated this here. I doubled the energy, and then I divided by 15,000 to get this, which turns out to be velocity squared. Last part, ladies and gentlemen, last part. So with the last part, ladies and gentlemen, we are going to take the square root of 1950.2, okay? And we walk away with 44.16 meters per second. That's how fast the rock is coming on Edward's tomb at the rooftop. Okay, that's it for the chapter and looking at the conservation of mechanical energy. I'm hoping that this will benefit you. This is Jonathan Grendel saying, wishing you many benefits. Take care.